Welcome to Basics of Metrology Part 1. I'm Richard Leach. I'm a Professor of Metrology. Been working in this field now for 30 years, so it really is part of me. I hope you can get a lot out of this course. It is one of the very popular courses on the CDT course, so we hope that you can learn a lot and that you can apply the skills when you get back out into industry or academic or whatever job you choose. So what will you learn in this first lecture? So I'm going to go over what metrology is, why it's needed, why it's pervasive in almost everything we do in life. What is this important concept that we call traceability, which is basically the ability to say that we're getting our measurements correct. We'll go over the key terms and definitions, a somewhat dry subject sometimes, but hopefully we can make it interesting, and it is extremely important. And then in the second lecture, we'll go on to the metrology legal infrastructure, which allows the different countries to enforce traceability, and the System International, which is the system of units. Okay, firstly, there's some background material. All of the material which I'll present here is available through the library, or you can purchase your own copy, of course. This one is Fundamental Principles of Engineering Nanometrology by myself, published in 2014, or second edition was published in 2014. The original was 2010, I think. In this book, you've got almost everything that's covered by the course, but it's only in it's not in too much depth, so it's a good background reading in general in metrology, and it will cover everything in the course, but some of the more in-depth stuff you would need a deeper text. Then there is Basics of Precision Engineering, which was published a couple of years ago with my co-author Stuart Smith at the University of North Carolina at Charlotte. So this is the first edition. It's probably the only basic textbook there is on precision engineering, and each chapter has questions and answers. There's a whole chapter on metrology. Chapter 2 is on metrology, and then there is a whole chapter on uncertainty analysis. And I can recommend the chapter on uncertainty analysis, and in fact many of the lecture courses we'll do in the latter part of the course are based on that chapter. Okay, some other background material which is available, and this is free, so you can go to the MPL website and download all of these guides, and there's many more as well, and I couldn't recommend them more. They're excellent guides. They're written more for metrology practitioners than students, but they have very, very useful background material, and I'd certainly recommend these if you do any work after your studentship that's based in metrology. So this one's Fundamental Good Practice in Dimensional Metrology. So again, covers much of what we talk about on the course, and it's by David Flack and John Hunniford, and published in 2005. So you can go and download that. And as I say, there's many more. So metrology, let's talk about some of the basics. So we can't get more basic, so let's define what we mean by metrology. Now, when I talk about all the definitions and terms that I'm going to speak about, they're all included in this document you can see on the right, which is the VIM. That's the vocabulary in metrology. Now that was published by the BIPM, the Bureau International des Poids et Mesures. That's published, available again, freely downloadable on the web. Make sure you get the 2012 edition. There are 2008 editions floating around, and the terms and definitions have changed significantly since that one was produced. So make sure you get this version. So almost everything we'll talk about, terms, etc., they're all in there. And the nice thing is you can get that document, and then when you're talking to people, when you're writing specifications, when you're manufacturing, etc., you can say, right, let's make sure we're all working to the VIM, and then everyone understands what definitions they're using. So what is metrology? Metrology is the science of measurement and its application. Many people quote it as just a science, but it's not. It's how you apply that science. What it is not is the branch of science concerned with the weather and the atmosphere and those sort of things, so what we usually call meteorology. Although if you do decide to be a metrologist, you will definitely get asked questions about the weather occasionally, because many people get the two terms confused. So let's talk about a little bit of history. It's debatable who were the first nations or countries to develop a metrology infrastructure, but and I think probably the winning at the moment is China as being the first. But the Egyptians have a very well-known measurement standard. So this is what's called what you can see examples here. The pictures are what's called cubits or subsections of cubits, and the cubit was defined as the length measured from the pharaoh's elbow to the tip of his finger tip. Now notice that, of course, that's a highly variable measurement, and if he's relaxed or not relaxed, or is put on some weight or something like that, then it's going to be a different length. But you then produce a material standard from that length, from the original length that is measured, and that's part of the definition. Then you realize that definition using a material standard, which is the cubit. And then the cubit was used to do absolutely phenomenal things. So the cubit was used as the basis for the measurements standards and standards infrastructure that was used to build things like the pyramids. The pyramids are phenomenal. The tolerances on the pyramids are pretty close to modern manufacturing tolerances when we scale them down, and people have said that it's just not possible. The sort of tolerances they got, I don't necessarily mean the global tolerances of the pyramid itself. I mean the tolerances of the separate blocks and the parts that were required to actually put the thing together. The tolerances are so high that people have seriously suggested and written books on the fact that there must have been space aliens came down and helped us do it. However, my own feeling is that actually it was done because they had a really effective metrology infrastructure in place. And in fact, if the metrologist wasn't following the national standards of the day, then the punishment could be death. So it was rigorously applied metrology infrastructure. But let's just look at some of the specifications on the left there. So you've got nearly 600,000 stone blocks weighing up to 30 tons, in fact some of them up to 70 tons. So I mean, just the logistics of moving the damn things is incredible. And then the casing stones were polished flat to an accuracy of 2.2 millimeters, so that's 200 microns. That, even if you could do that now on a metal block in a modern manufacturing industry, or a glass block, for example, in modern manufacturing industry, is a phenomenal tolerance. So how they did that is still probably not completely clear how they got those sort of tolerances. We're talking serious skill here and practice. But more than just skill and practice, it's having the ability to confirm that you're getting the correct answer, that you're hitting those tolerances, basically. And then there were others, for example, the casing stones, up to 20 tons, and an accuracy of that were placed within accuracies of 0.1 millimeters. So incredible tolerances, really. In England at the time, probably our first proper metrology infrastructure was the Magna Carta in 1215. And this attempted to standardise measurements throughout the kingdom, and it mainly concentrated on wine and beer. Now, why, you might ask, would it concentrate on wine and beer? Well, in those days, the water was such poor quality that most people drank wine and beer. That's all you could drink, because it was sterilised to a certain extent. So people would literally get up in the morning, and if they cleaned their teeth, they would do it in their beer. So it was an important measure, and they had to have some kind of infrastructure in place to make sure people were getting the right volume and the right mass of the products that they were selling. So we're a little bit behind the Egyptians. In China, and China probably goes back at least 3,000 years or something like that. And here you can just see some examples I've gathered from just from the web of mainly standards which are used for mass, But you can also see there you've got this standard here, this right angle here is a standard of squareness, effectively, or perpendicularity. So all of these would have been used in manufacturing, in selling products and things like that. So if I've just listed a few examples here of where we use metrology in the modern world. So, for example, food and raw materials are bought by weight and size. Water, electricity, and other amenities are metered. Healthcare, hugely important these days, of course, relies on medicine dosages and samples analysed. Law and order, tolerances on speed vehicles. Some of us have been unfortunate enough to suffer from those tolerances, and fingerprint recognition systems. Your safety relies on setting smoke alarms. So smoke alarms are effectively radiation detectors usually. And then the environment is constantly monitored for air quality, weather conditions and things like that. So that's, if you like, the last one is where metrology meets meteorology. So it's ubiquitous across almost everything we do as a modern society requires some kind of measurement system. So if we're going to do all these measurements, we need something in place. We need the infrastructure, and the things I'm going to talk about in these first really 4 lectures. We need these infrastructures in place to allow us to be able to do these things. It can also go drastically wrong if we don't do our metrology correctly. So here you've got an example, and some of you might remember this, I certainly do, when the NASA's Mars Climate Orbiter, I remember we all gathered I used to work at the National Physical Laboratory, and we all gathered sitting there watching it land, basically. So we saw this live as all the staff. So the Mars Climate Orbiter spacecraft crashed, and the simple reason that it crashed is because the Americans were using the imperial units or English units, and we were using metric units. So and we supplied some information that went into some modelling, which went into calculating the trajectories, etc., and therefore it crashed. And so a lack of metrology there cost probably well over $125 million, and a lot of heartache as well. Some people work for 10 to 15 years. People tend to work on these types of projects, and it's disastrous when they go wrong. So that's a metrology problem. Here's the second one. Again, some of you might remember. Again, I certainly do. I know people that worked on the committee afterwards. This is the Hubble Space Telescope, and this was going to be the most amazing telescope that went up it to look at the beginnings of the universe, etc. And it went up there, they got it up there, and it didn't work. So it was giving defocused images. And after many discussions and analyses, they found that there were 2 problems. First of all, the measurement system that was used to measure the primary mirrors, the main mirror segments, had some residual dust that was left over that was causing a significant problem. Now, that may not have caused the problem itself, but what they didn't do is then compare against previous measurement methods which had been used for years. They didn't compare the two because they thought, well, this new method is much better. We don't need to compare against the old method. Because they didn't. If they'd compared against the old method, and comparison is extremely important in metrology, then they would have realised that they were getting the shape wrong. So of course they then had to spend multi-millions of dollars sending astronauts up to apply a correction, which worked incredibly well, but it was a serious feat of human endeavour just to get it working again, but it was unnecessary. So what is traceability? This is a term that you'll get used to. We talk about a lot in metrology, and it is basically the way we can say that a measurement is correct. So what do we mean by that? And by far the easiest way to talk about this is to give you an example. So let's assume that I'm manufacturing phone cases, and I want to measure the width of my phone case. And I want to do some quality control on that, or to make sure I'm producing the parts correctly, to make sure they can be assembled later down the line, and also to show that my process is staying in control. So how might I measure that phone case? Well, I might use one of these, either a caliper or a micrometer there. Note the better design there. I'll leave that to you as to why that's better designed. Okay, so let's assume in this case we're using the caliper. So I use my caliper. I've got maybe a accuracy on the caliper is quoted to something like 10 microns or something like that. That's enough for me to control the tolerancing on my phone cases. But how do I know, with my hand on my heart, how do I know that I'm getting the right answer there? How do I know that the width of the phone case I measure is correct? So there's me using the caliper to measure my phone case in my office. That's a couple of years old now. I remember I had to give this lecture at 9 o'clock. I'd forgotten to take the photo, so I got the cleaner to take the photo of me first thing in the morning. But so there's me measuring with the calipers. But how do I know? Even though I've got stated accuracy, I need some way of testing or knowing whether that measurement is correct. So what I tend to do is I would apply some kind of comparison. So I use my calipers to measure something more accurate that I do know the accuracy of. And this process, that process of checking against a reference, that process is called calibration. We'll talk about that a bit later. So here I've got this box of gauge blocks, or sometimes people call these slip gauges or just gauges. So you've got 122 gauges in a typical box, and they're what's called end standards, which means you measure from end to end. They've got highly polished and parallel end faces. So on the right there, you can see me holding two gauge blocks. Now they appear to be glued to each other, or somehow they're contacting each other, but actually there's no gluing process going on there. What's happening is they're so well produced, they're so flat, but not too flat. They're flat enough that when you join them together using a sort of ringing process and a little bit of fluid, years ago, people used to take a piece of a little piece of grease from their neck. These days, you can buy ringing fluid, but a little, very small amount of fluid. You push the two surfaces together, and they ring. You get a very, very good contact, and you can see, nothing's holding that up on the right. So it's staying there by pure contact alone, what's called ringing process. But anyway, that aside, with that set, I can make any length from the very smallest gauge block in there to all of them joined together, and lots in between. And they're specially designed so that you can do a huge range of different lengths you can produce with this set. But there's a question, or another question. How do I know that the gauge blocks are correct? So I've got a certificate with them, but how do I know that that's giving me the right answer? So typically the gauge block would have been compared against a reference gauge block, so that's another calibration process, using what's called a mechanical comparator. And you can see one of those on the left, and you can see it's schematically shown on the right. So you've got your standard gauge block and you're comparing against your unknown. And this is a beautiful way of measuring, because you're only really measuring that difference. So your length measurement becomes a very small measurement in essence, and it means that systematic errors, which we'll talk about a bit later, are blocked out. But we're going to do this in lecture 4. We'll do this as an uncertainty example, and you'll see exactly the benefits of using the comparator principle. So we compare against this reference gauge block. That's all well and good, but surely there's another question. How do I know that that reference gauge block is correct? How do I know that the result I get with that is correct? Well, typically the reference gauge block would have been calibrated using this thing on the left you can see, which is, so there's the gauge block itself, which has been run to a base plate and put into an interferometer. Now, I don't want to go into the principles of interferometry. You will cover those a little bit for surface measurement later in the course. However, let's just say interferometry is a way of measuring length, L, in terms of wavelengths of light. So it's a number of wavelengths of light. So if we look at the equation, the length equals the wavelength of light divided by 4 pi. Don't worry about 4 pi, that's convention. Multiplied by this delta phi. Delta phi is a phase angle. So it's an angle. So the units there are length measured in meters, wavelength measured in meters. This is unitless because it's an angle. So we basically measure length in terms of a number of wavelengths, and that's typically not an integer number. That will be a non-integer. So it will be an integer plus a fraction, and that fraction is determined by by this value here. So effectively we are measuring length in terms of wavelengths of light. So that's nice because the wavelengths of light they don't vary too much, but they do vary. So I do need to ask the question, how do I know that the wavelength of light is correct? Well, this process has got us. We can't just keep going on and on and on and on and on and getting more and more accurate as we go. The buck has to stop somewhere. And this is where it stops. So how do I know my measurement correct was the original question related to the phone case in my office. Well, perhaps the real question, and remember that the wavelengths were measured in meters, what is length? What do we actually mean by that? Well, quite simply, the definition of length is that is measured in meters. So perhaps the real question we're trying to ask here is, what is a meter? And we'll cover that in some depth. So hold that question in the back of your mind. We're going to think about what we mean by a meter, and that will help us go through that chain of measurements, and I'll show you a picture of that chain in a minute. So many years ago, around 1790, we as an international society decided we need something better than a Pharaoh's cubit or the Chinese measures. We need something that isn't a material standard. Now, the problem is, and we'll cover this in more depth later, but material standards, they can change in length. And if your basic length standard, your meter standard changes in length, then every length measurement across the planet, which compares back to it, changes. So you need something which hopefully doesn't vary. So we tried to come up with something, basically looked at all the physics, and there were many proposals, some by some very famous scientists, the Rayleighs and Thomsons of the world, who came up with ideas for things that don't vary with time. But the one we came up with, and I have no idea why we chose this one, was 1/10 millionth part of a quarter of the Earth's circumference. That was going to be a meter. So two guys, and this is a brilliant story. I thoroughly recommend you reading this story. Two guys, they surveyed from Dunkirk to Barcelona. It took them over 10 years. They were imprisoned. They were involved in wars. They both nearly died on several occasions, but they did it, and they got the surveying from Dunkirk to Barcelona correct to about 4 millimeters, something like that. But and that allowed, when they then subdivided that value, it gave them the meter, the 1/10 millionth part. Of course, once they'd done it, humans around the world had realised that this is a pretty stupid thing to do and almost impossible to realise in practice. So we went back to a meter standard, or a meter bar. So now we're back to a physical bar, which is kept in a very well controlled environment. It's very nicely made from platinum. It's an end standard again, so we're measuring from end to end, and that was employed up until about the 1950s, when we went to effectively the modern definition. So what is the modern definition of the meter? How do we define the meter? Because we wanted to get rid of that bar. So we did that. And this was the definition up until March last year, and I'll talk about why that date's significant. But the meter is the length of the path travelled by light in a vacuum during a time interval of 1/299,792,458 of a second. So a couple of things. Let's just pull that apart. So first of all, it's if we think of the equation that speed equals distance divided by time, the time is 1 over 299,792,458, which is, let's just call that value c. So it's 1 over c, where c is the speed of light in a vacuum. So we need to be able to determine a time interval, 1 over c, and then we can plug that into the speed equals distance over time, and the distance that will come out will be a meter. So it's very simple to define what a meter is in terms of a fraction of the speed of light in a vacuum. It's important to say in a vacuum because the speed of light actually will be a different value to that if you put it into air, for example, because you get a refractive index change, which modulates the speed. So that was the old version. Now, so that became the definition of the meter. Now, somehow we've got to link that to our chain of measurements that we're doing. And, we've got to get all the way to me in my office measuring the phone case with the pair of calipers. So you have to have some kind of realization of that definition. And the way we do that is we take advantage, and we'll cover this in a little bit more depth in the next lecture, but we take advantage of what's called the dispersion relation, which is the speed of light equals the wavelength times the frequency of the light. And from that, if we say that we fix the speed of light, and we can do that, and Einstein told us that it doesn't vary throughout the universe, we fix the speed of light in a vacuum, then if we also fix the frequency, and we can use what frequency stabilized lasers, and that's what's done, is a frequency stabilized laser, and then the wavelength can be used as our effectively as our meter ruler. And we can get this, so you can use a frequency stabilized laser, locking it to an atomic transition, which gives you a quantum mechanical definition effectively of the definition of the meter. And we can do that to about 2 parts in 10 to the 11. I'll come on to what I mean about that in a minute. So now we've got a laser which has realized the definition of the meter. What we can then do is compare the laser we use on our interferometer against this reference laser. Again, we've got a comparison. We've got an unbroken chain of comparisons from the definition of the meter to me in my office. Here's the new version. Don't worry too much about that at this stage. We'll cover that in the next lecture. It's effectively the same. So how do I know my measurement is correct? The answer is via this traceability route. So traceability, we got the international standard at the top there. So that's the definition, that's the meter. Then we got the industrial standard. So that could be the interferometer. So the interferometer measures the reference gauge block. The reference gauge block is used in the comparator. Comparator measures the gauge block, which is used to calibrate my calipers, which are used to measure the phone case. So that's the unbroken chain of comparisons up to the definition of the meter. So let's look at it. We've got me in my office using the pair of calipers. Calipers are calibrated using gauge blocks. The gauge blocks are calibrated using a mechanical comparator. The mechanical comparator is calibrated by a reference gauge block, which is calibrated via an interferometer. The interferometer uses a laser source, so we know the wavelength. The wavelength is calibrated against the reference wavelength, which is used to realize the definition of the meter. So that's it. There's our unbroken chain of comparisons all the way from my office or a manufacturing environment to the definition of the meter, which would typically be held at one place per country. And then we compare all those. So if we look at these values we put here underneath the pictures, these are the relative accuracy of the measurement. So here I've got, if it was 1 part, it'd be 10 to the 5 in a meter. So that I've got an accuracy there of about 10 microns, something like that. There's about a micron, they're about 0.1 microns, 0.01 microns, 0.001 microns, so that's 0.1 nanometers now, and then we can realize the definition of the meter to about 0.01 nanometers or 10 picometers. So the accuracy of the measurement has to increase as you go from the thing you're actually measuring in industry to the definition. Okay, so that was the meter, but there's a whole bunch of SI units which are required to realise a full measurement infrastructure for manufacturing and daily life, but we'll cover those in the next lecture. So we're now going to go over the terminology that's used in metrology. Again, it's a rather dry subject, but it is absolutely essential that you get these things right. You can't really be talking to people if you're effectively using a different language. So if I'm talking about precision when I mean accuracy and you're doing the opposite, then we've got a problem. And that's when, spaceships can fall out the sky, etc. So we have to get our terminology correct. It's almost as essential as having that traceability infrastructure. So once again, you can get all these terms in the vocabulary in metrology, the VIM 2012 edition. You can download that from the BIPM site. The first one to note is the definition of the measurand. The measurand is the quantity intended to be measured. So in my case, it will be the width of the foam. Two other terms, true value and error, which are highly related to each other or intimately related to each other. The true value is a hypothetical result that would be returned by an ideal measuring instrument if there were no errors in the measurement. And of course this cannot exist because there always are some errors. So first of all, it's impossible to avoid any forms or all forms of error. But let's assume you could. So for some reason you could completely decouple your experiment from the environment and you were able to have no sampling errors or anything like that. Then you would still have quantum mechanics coming in and Heisenberg's uncertainty principle would kill you. So the true value, it's an important concept, but it's only conceptual. It doesn't actually exist in reality. So we always approximate the true value. The error is the measured quantity value minus the reference quantity value. Now, often the reference quantity value is the approximation for the true value. So the error is usually the measured quantity minus the true value. It's always present. As I said, there's always some form of error, and we split errors into systematic and random errors, and I'll talk about both of those now. They're closely related to the terms accuracy and precision, as you'll see as we move on. So the error is the difference between the result of the measurement and the true value, or the reference value. Since the true value cannot exist, as we've said, then in a way, the error doesn't exist. Well, it's not that the error doesn't exist. A completely defined value for the error never exists. There's always some what's called uncertainty, and we'll cover that in later lectures about that value of the error. So a conventional true value is used in practice. So normally we would approximate it with something like a mean. But again, we'll cover all of this. Relative error is obtained by dividing the error you get by the mean of the measured value. So typically you'll find relative error is quoted in terms of percentage, so percentage of full scale or something like that. Two types of errors are random errors and systematic. So random errors, so these are the effects that are always present. There's always some random errors, and again, at the very, very heart of it, there might be quantum mechanical fluctuations, but even if normally those are swamped by things like vibration, thermal fluctuations, electrical noise, and many, many different types of error source. Typically, if you did repeat measurements, so you just kept repeatedly measuring the length of the phone case, for example, then you can plot the distribution of those results, and you'll usually get some kind of bell curve or some kind of distribution if they really are randomly distributed. So how do we minimize them? Well, we can address the issue. So if it's a thermal issue, we might put it into a thermal enclosure or control the temperature. If it's mechanical, we might put it onto a vibration isolation system. If it's electrical, we may address the noise sources by looking at proper grounding and things like that. So there's many textbooks, etc., on how to minimize random errors. So we address them directly. Or another way to address them is to take repeated measurements and then calculate the average. If your errors were only randomly distributed, then you can decrease the errors by a factor of the square root of the number of measurements you take. But we'll cover that when we talk about the uncertainty part of the course. Systematic errors. So these are errors which are not randomly distributed, but are more like something like a bias. So I effectively get the wrong answer by a certain offset or something like that, or a gain error in an instrument. So these are typically instrumental, physical, but they can be human as well because you've not set the system up properly. So how do you minimize them? You can use what's called adjustment. And adjustment is another word that's used for adjustment is correction. So you apply an anti-bias, which is the negative of your positive bias, and correct it back to zero. And that, if you think about the measurement that we were doing with the comparator, that's exactly what you're doing. You're using the reference gauge block as a form of adjustment, so you've only got the systematic error left. You can use careful calibration techniques and, of course, the best possible measurement and good practice that you could apply. Typically, the way we represent a systematic error, it would be, and you can see the difference between these two distributions, the difference would be the systematic effect. And each of them, you'll notice, has a bell curve because it will also have some random errors as well. Accuracy and precision. These are two terms which you will find throughout your career, people use almost, they intermingle them to a high degree, unfortunately. But you're not going to do that. From now onwards, you're going to use these terms correctly and correct other people when they don't use them correctly. So accuracy is the closeness of agreement between the measured quantity value and a true quantity value, or reference value. So it's extremely close to the concept of error. And if we look at this little graph down the bottom here, you've got if you're doing, again, repeat measurements are being done. This is the value that you're getting over here. If the value you expect is this reference value here, and what you get is the value on the bell curve, in the middle of the bell curve, then that quantity there is your accuracy. It's the difference between the reference value and the value you get. The precision, on the other hand, is the closeness of agreement between indications or measured quantity values obtained by replicate measurements on the same or similar objects under specified conditions. In other words, if you just repeat and you make sure that your environment isn't changing too much and that there's no changes in the measurand, then you do repeat measurements, and the spread of those repeats, so some kind of deviation, usually a standard deviation of the repeats, will give you the value for the precision of the measurement. So down the bottom here, you can see the target. So if that was an archer who was, and let's say our true value is the center of the target, then the one on the left there has high accuracy because it's spot on the true value, and and high precision because they're very close together. The second one on the left has high accuracy because they're pretty close to the target, but they're not so precise. The third one, second from the right, has low accuracy because they're not really close to the target value, but the precision is good. And then the fourth one has low accuracy and low precision. So I hope that's clear. I really can't get it across much. This is extremely important to get this right, especially in manufacturing industry. Let's just talk a little bit about accuracy. We can split it into a number of 5 basic components which will all add together to affect your accuracy. And many of these, you'll notice, will cause systematic effects. So first of all, the factors affecting the calibration standards. So the standard that you use as your reference. So you might get, if it was a bar, there could be thermal expansion, the time in between your calibration intervals. So if you're getting an external party to calibrate it for you, you need to watch that you're within the time that they suggest that you need to have it recalibrated. So that relates to the stability with time. It could be elastic properties if you're using mechanical probing, etc. Secondly, the factors affecting the object being measured. How clean is it? If it's not clean, then you're using if, for example, my phone case wasn't clean, then I'll get errors in the measurement using the calipers. The surface texture of the part I'm measuring, if there's defects in it, elastic properties, how well is it supported, etc. Factors affecting the inherent characteristics of the instrument, scale error, friction, hysteresis, drift, calibration, and repeatability. 4, the factors affecting the person who carries out the measurements. Are they trained correctly? Do they have the appropriate skills and experience? And lastly, the factors affecting the environment. And here you could, the main one is often temperature, especially in dimensional metrology, simply because of expansion. So radiation, expansion, gradients in the temperature, but there could be problems, could have humidity, vibration, cleanliness, and things like that. Another important term is resolution. And you need to be a little bit careful here because resolution is often used in terms of optics. For example, when people are using cameras for imaging, they talk about resolution of the camera or the CCD array, etc. This is not the same. So resolution in metrology is the smallest change in a quantity being measured that causes a perceptible change in the corresponding indication. A good way to think about that is in terms of this ruler. So it's the smallest indications you can see on that ruler. Often you would say that it's half of the distance between the two that you can see well. Another way to think of it is if you had a digital multimeter, for example, and then the last unit, which is usually flashing around due to random errors, that would be the resolution of the instrument. It's often called discrimination. But beware, it's not the same as optical resolution. We will talk about optical resolution in later lectures. So here's our formal definition. This is straight out of the Vim of calibration. We've talked about it quite a lot so far already, and I'm going to give you my simple definition in a minute. But let's read this one out. The operation that, under specified conditions in a first step, establishes a relation between the quantity values with the measurement uncertainties provided by measurement standards and corresponding indications with associated measurement uncertainties, and in a second step uses the information to establish a relation for obtaining a measurement result from an indication. Now, I don't know about you, I find that extremely difficult to read and understand. So I'm going to put it a little bit simpler for you. Calibration is a comparison between two measurements, one of which is a reference or a standard value, the other which is being tested. So, in other words, it's that calibration step. But an important thing here is that in the formal definition, it states about uncertainties. You cannot compare two things unless you've got an understanding of what uncertainty is. And so we'll cover uncertainty in a minute. But you can't have calibration without uncertainty, same as you can't have traceability without uncertainty. So another important term is adjustment, and we talked about that briefly earlier. So it's often called correction. So it's a set of operations carried out on a measuring system so that it provides prescribed indications corresponding to given values of a quantity to be measured. What that means in plain English is that if we've got some kind of systematic offset with our instrument, we can correct it back. And you might do that by mechanically adjusting the instrument, or you might change it in the software or something like that. Verification, often mixed up with calibration, is the provision of objective evidence that it gives that a given item fulfills the specified requirements. In other words, that the instrument is doing what it says on the tin. So a little bit more about calibration. So another way to say it is a comparison of an instrument performance to a standard of known reference or to a reference value. Benefits in manufacturing should be pretty clear. So it increases production yield because it optimizes resources. So it means that you are getting your measurements correct. You're not producing duff parts. You're not going to have to do so much scrap or rework. It assures consistency between the parts you're manufacturing. It allows you to assemble parts, assures measurements and possibly products are compatible with those made elsewhere. That's highly important. If you can imagine you're buying in parts for a complex assembly from China, then you need to know that that they have calibrated their system and that you're all working to the same metrology infrastructure. So measurement uncertainty, we've discussed it a few times. In fact, we've got two quite detailed lectures on the subject. It can get quite mathematical. It's pretty simple mathematics, but you do need to understand it to be able to do uncertainty calculations. So no measurement, as we've discussed, is ever guaranteed to be perfect. Uncertainty of a measurement is the doubt that exists about the result of any measurement. There's always some doubt. And what we try to do with uncertainty analysis is quantify that doubt, put a number on it. So by quantifying the possible spread of measurements, we can say how confident we are about the result. The formal definition, actually not in the, I don't think this is in the VIM, it's in what's called the GUM, which we'll talk about when we talk about uncertainty. So it's the parameter associated with the results of a measurement that characterizes the dispersion or the spread of the values that could reasonably be attributed to the measurement. Okay, so that's pretty much it for the first lecture. Going back to the first slide, we've covered the metrology and why it is needed. I hope I've convinced you. We've looked at traceability and we use the definition of we use the example of my phone case for that, and we've gone over the key terms and definitions. What we'll cover in the next lecture is the legal infrastructure that's in place to ensure that we do these things. So in the case of the Pharaoh, it was the death sentence, but it's not quite so tragic these days, but there is a legal infrastructure in place. And the System International, which is the international system which allows us to say that we're using the correct units. Okay, thank you very much.